nanoHUB.org.
Online simulation and more for nanotechnology.
Okay, let's continue. Today we have this concluding lecture actually on materials for enabling plasmonics and metamaterials, material platforms. And this plot shows various materials as a function of 3 coordinates actually. So on this axis I'm showing the wavelengths at which material becomes plasmonic. And remember that material we call plasmonic if the electric permittivity, the real part, is negative. When it's negative, you could excite surface plasmon resonance. And when you do so, you can confine light down to nanoscale. And that's the key thing about plasmonics. So on this axis, I'm showing the imaginary part of the electric permittivity, which describes losses. Losses, as I already mentioned, not necessarily detrimental. It is a problem when it comes down nanophotonic circuitry, but for example, it's a huge advantage actually when you do this nanoscale heating, which is important for a number of applications. And finally, in the third vertical axis, I'm showing the bulk melting temperature. Why it's important? Because, as I mentioned already a couple times, that when you confine energy down to very small volume, you have high concentration of energy, and therefore you elevate temperatures. And your material should sustain elevated temperatures. Otherwise, of course, your device would be broken. Even though I'm showing here the bulk melting temperature, and in reality, problems become at much, much smaller temperatures, simply because when you're working with nanostructures, there are other phenomena such as creep, such as change in shape, diffusion, softening of material. But they're all proportional to the bulk melting temperature. So the higher the bulk melting temperature, the more robust, the more refractory your material. Remember, refractory means that the ability to sustain elevated temperatures, high temperatures. So what you could see here, that's the commonly used until recently plasmonic materials, silver and gold. They indeed indivisible become plasmonic. They are shiny. They have this metallic luster. They reflect light. Aluminum. And but the problem is their bulk melting temperature is very low. Therefore, when you nanostructure these materials, even at relatively low intensities of light, the temperature locally increases up to 350, 400 Celsius, and that's enough actually to bring damage to your nanostructure. So, which precludes this durable using of this device. On the other hand, you have this material such as tungsten, which is a well-known material which can sustain very high temperatures. But the problem is it's not really plasmonic, at least not in the visible and not in the near infrared. Or you could say that it's barely plasmonic, so it's not really used as a plasmonic material. And this is new materials which our group pursues and some other groups. Transition metal nitrides, as I pointed out, are basically ceramics, materials, plasmonic ceramics, which are plasmonic. You could see that in the visible around 600, 500, 800 nanometers, they become plasmonic. The electric permittivity is negative, meaning that they can support surface plasmon excitations and then enable confined light down to nanoscale. But they're also refractory. They are as refractory as tungsten actually, and that's really important. So this new material, they are plasmonic. They basically pretty much mimic plasmonic properties of gold, for example, but they have very high melting temperatures and they are hot. So therefore, one could say that transition metal nitrides can be the solution for high temperature applications. And the point is that even your application is not intended to be high temperature applications. However, because if you confine light down to nanoscale locally, even the ambient temperature still could be room, but locally you do elevate temperature. So it is very critical that your material can sustain elevated temperatures. And here I'd like to review with you some key applications of these plasmonic materials, new plasmonic materials. One could argue they're not really traditional. They're not intended in this case for nanophotonic circuitry or sensing. They are more like based on the ability to locally heat. And that's actually very important to locally provide heating. So, and I mentioned these several applications, solar thermophotovoltaics. This is energy related. data storage, heat-assisted magnetic recording, photothermal therapy, and I still say a little bit about nanophotonic circuitry and nonlinear optics because these materials are good in that regard as well. So that clearly seems to be a really important material platform for all this type of applications. So let's start with these local heating applications. So what we did Urchan Guler, actually, my postdoc at that time, he was a student. So it's a very simple experiment. We would make a disk of gold and disks of titanium nitride. When we irradiate it with light and measure the temperature increase. And we clearly obtained that with titanium nitride, actually, temperature increases more, meaning that they could provide more efficient local heating, which is important for a number of applications. So it clearly shows that titanium nitride could heat more effectively, more efficiently than gold does. And I will show a number of applications where it matters. So my former student Satoshi Ishii, who is now one of prominent researchers in Japan, so when he left the group, he also made this demonstration where he showed that titanium nitride actually overlaps with sun spectrum much better than, for example, carbon, not speaking of gold. Not speaking of gold. So, which means that it could be very good material to use for these solar energy applications, basically to convert solar light into energy. And also he did this experiment where he showed that indeed titanium nitride heats more efficiently, in this case water. When you play these particles of titanium nitride or carbon in water, you could see that titanium nitride heats more efficiently than carbon does. So that clearly indicates that this material, besides traditional plasmonic applications, could be also used for energy conversion. And that work done largely by Urchan Guler, whom I mentioned already. That's about this energy applications. So let's first recall this photovoltaics, how it works, and what are the challenges there. So with photovoltaics, we convert energy coming from solar light into electricity by using the photovoltaic cells. Basically, photons are absorbed, converted to electron-hole charge pairs, and these charges are separated, and that's generate electricity. So, but clearly all the photons which are below the band gap of your photovoltaic cells are not absorbed, they are wasted because the energy is smaller than the energy over band gap. And also those photon energy which have energy much larger than band gap, the efficiency of conversion is not as high as for photons with the energy matching the band gap. So because lots of energy goes into heat in this case. So, and as a result, we know that for this, for example, silicon photovoltaics, the conversion efficiency ideally around 30%, but what you buy is around 20%. On the other hand, it's well known theoretically that if you use a little bit different approach, if you simply heat up your object, and to heat up your object, you could use the sun, or actually any source of heat, like wasted heat, or I don't know, like fuel. So if you heat it up and let radiate it, black body radiation, if temperature is high enough, that conversion efficiency could be very high. Basically it's like a Carnot cycle. So it's the temperature of the high object minus temperature of cold object normalized by the temperature of the high object. So, and in this case, let's say if you heat your object up to roughly, let's say 1500 Celsius, and your photovoltaic cell at room temperature, the conversion efficiency could be as high as 80%. So, and the question is how you could control the radiation of this black body, because it radiates everywhere. And it's well known that with plasmonics, with like antennas based on plasmonics, you actually could enforce your emitting object to emit in a particular spectral range by introducing these resonance structures, so that that light would be emitted at wavelengths matching the band gap, and then the conversion efficiency would be optimized. Well, and all photons which do not match the band gap, they basically would be recycled. That's a simple idea. And with plasmonics, you can do it. The challenge, and actually it has been demonstrated, for example, by Bajivol a long time ago, but the challenge, of course, with plasmonics, conventional plasmonics, you cannot heat it up up to these high temperatures. So if you would like to go up to 1500 Celsius, forget about plasmonics if you use conventional plasmonic materials. So as I mentioned, the bulk melting temperature 1000, but when you nanostructure it to make this frequency selective emitter, even 500 Celsius would destroy it. So the solution is to use these refractory plasmonic materials, which you could heat up above 1000 Celsius and which could work as a frequency selective emitter, so that your black body would emit light only matching the band gap of your photovoltaic cell, so that the efficiency would be optimized. So to elaborate a little bit more, this is black body radiation of 1500 Celsius object, which you heat up to 1500 Celsius. If you put now here the typical photovoltaic cell, like in this case gallium antimonide, so you would see that overlap with the spectrum of radiation emitted by black body is very small, only 22%. So the efficiency would not be really high. However, if I put this frequency selective emitter made of good refractory material that can sustain these high temperatures, then actually it's like 53%. You basically, what you do, you reshape the emission for better match. So in this case, you could count on 53% conversion efficiency. That's actually beats already photovoltaics, and that's very real. So the only thing you need just to heat it up. As I said, you don't need even sun for this. Or you could use hybrid technology, sun during the daytime and fuel during the nighttime. And you just heat it up to high temperature, put this frequency selective emitter, which would allow emit only in particular frequencies. And you could count on very high conversion efficiency. So Urchan is working now on building prototype of this solar thermophotovoltaics, which in principle could be a breakthrough for this energy conversion, because it's not a secret that most of energy around us, it's actually wasted heat. If somehow we would be able to use that and convert it to electricity, that of course would be very important development. And to further elaborate this idea, we would build a broadband absorber. This is, by the way, shows the absorption. You see, it matches. It's actually very well matches. It absorbs in the whole spectrum of the sun. And you could make it by simply using these rectangular rings made of titanium nitride. It's very simple. It would absorb the whole sun spectrum with efficiency close to 100%. And as for frequency selective emitter, you could use simple rods like shown here. And they would emit at the spectral range matching the photovoltaic cell. That's really important that the match is good. And to show that titanium nitride indeed is advantageous over gold, we would make this rectangular ring out of gold and simply heat it up here up to 800 Celsius. That's what happens to gold, not surprisingly. And you could see that nothing happens to titanium nitride. It's a stable material. Also, if you irradiate it with a laser pulse, so this pops out actually gold, and titanium nitride is nice and stable. And moreover, you actually could preclude oxidation, because that could be an important problem, by using some overcoat layer. And you could see that in air, you could heat it up, then cool it down, heat it up, and the spectrum is very, very stable. So meaning that it's really potentially good material for this solar thermophotovoltaics application. This is an example how materials make a difference. I mean, from the point of view of ideas, it was known that with plasmonics you could make these frequency selective emitters by putting all this type of antennas. But what was lacking the material, which you could heat up to these high temperatures, basically for these thermophotovoltaics, the higher temperature, the higher the efficiency. And with conventional plasmonics, you're really limited in that regard. So, but with this refractory plasmonic materials, it makes a big difference. So in all these studies, it's absolutely critical to take into account that the electric permittivity, the optical properties of plasmonic materials change with temperature. And that they were very limited studies, almost non-existent in that regard. And my other student, Harsha Reddy, made this absolutely important. I said that's going to stay in history because, I mean, everybody uses tabulated data on optical properties. But to know how they change with temperature, it's absolutely critical, because almost in any optical experiment, the temperature increases. But if you're doing experiments where you specifically want to heat up, then of course you particularly should take into account. And he showed that indeed, in these 3 papers published in 2 ACS Photonics, it's all recent, and 1 in Optical Materials Express, he studied gold, silver, and titanium nitride, very systematic studies as a function of temperatures, how real and imaginary part vary with temperature. And this is kind of busy slide, but the simple conclusion is that at room temperature, gold a little bit outperforms titanium nitride in terms of plasmonic properties. Imaginary part is somewhat less, not much, but less. However, when you heat it up at around 450 Celsius, titanium nitride actually becomes comparable to silver and gold. At higher temperatures, silver and gold simply doesn't survive normally when it's nanostructured. Whereas titanium nitride just remains stable and you could still use it. So that's a very important thing to know, how these optical properties vary with time. And now we are well equipped in that regard, thanks to very hard and systematic work performed by Harsha already. So yet another application that has to do with data storage, a very important one actually. It's a huge billion-dollar business, multi-billion-dollar business, which about recording information on all these hard drives, disks, and in this case, to increase the data storage, what you want to use smaller bit size for this magnetic grain. When you flip the magnetic moment, this is like your 1 bit. So if you flip it again, it's 0, 1, and 0. So that's the way you record information. And if you would like to place more in a more denser way this information, you have to use these smaller grains to flip the magnetic moment. But when the grains are small, actually coercivity becomes very high, meaning that it's harder and harder to flip the magnetic moment with a magnetic field, to the extent that magnetic field becomes not practical. So the idea what people use, and it was suggested long ago, that if you locally heat this particular grain, then coercivity drops with temperature. It means that even with moderate magnetic moment, you could flip it. So the idea to make your information to record it in a denser way is actually to use this heat-assisted magnetic recording. So you locally heat a very small grain, coercivity drops, then you apply the field, magnetic field, and you flip the magnetic moment. That's the way to record it. So, but to accomplish this local heating, you need to have this near-field transducer, basically antenna, which would allow very locally heat up your magnetic grain. So for that, people use this like optical fiber companies, like it's of course an important business like Seagate and many other companies. So you deliver light with through optical fiber, and that works as antenna, and you locally heat, drop coercivity, and record the information. However, since you locally heat, temperature elevated. And that's the problem. In principle, HAMR, heat-assisted magnetic recording, promises 10 to the 16th times greater these storage densities. But locally, when you heat, the temperature goes up to, let's say, 400 or even 500 Celsius. And when you have nanostructured gold, it can sustain this temperature. Again, that's a problem. And if you would replace gold antenna with titanium nitride, for which this temperature is nothing, then of course that could be the solution. You see, you basically changes the material, but it makes a huge difference for this important industry. So that's yet another interesting applications which we pursue in our group. Well, arguably one of the most important and one most demonstrated so far applications of plasmonics is for what people call thermal therapy. In this case, to treat cancer. So the idea is very simple. You take a particle, plasmonic particle, and deliver it to cancerous tissue. There are many ways to do it, by using some ligands, or just simply by sending them into bloodstream. And because cancerous tissue tend to be more porous, these particles actually tend to stay there. But one way or another, you could deliver these small plasmonic particles to the cancerous tissue. That's really not a challenge. Then if you irradiate it with light and excite these surface plasmons. So because you excite surface plasmons, there is local heating. And when you locally heat, you destroy this cancerous tissue. So you first deliver particles to cancerous tissue, then irradiate it with light, but you have to irradiate it within the what's called biological transparency window, so that light wouldn't be absorbed. Our body is largely water. Basically, it's a transparency window for water. to a large extent. So it's between, let's say, 800 and 1200 nanometers. That's where you would like to radiate, so that light would go through the body. Excite surface plasmons in colloidal particles, plasmonic particles sitting in cancerous tissue, locally hit it and destroy it. Lots of pioneering studies in that regard has been done by the Halas group in Rice. So what they use, it's gold nanoparticles. But if you take conventional colloidal gold particles, the plasmon resonance is outside of the biological transparency window. For gold, it's around 540 nanometers. So it's not really in the biological transparency window. What they do, they instead of using this colloidal particle, they use nanoshells. Basically, it's a dielectric core coated with a gold shell. So, and that shifts the resonance because it's not a sphere anymore, it's a shell, it's a dielectric core and a gold shell, and that shifts the resonance to this biological transparency window. But when you make, in a chemical way, these nanoshells, they actually become relatively large, 110 nanometers, and when your colloidal particle large, it could be a problem because they could stay in your liver and kidney. It's harder to remove them from the body. And also use all this type of surfactants to make these particles chemically, which make this particle even stickier, more sticky. So, and with titanium nitride, in contrast, if you do nothing, if you just take colloidal particle of titanium nitride, no structure, so they absorb exactly in biological transparency window. You don't want to shape them in any way. They already absorb in the range where it's needed. And you don't cover it with any surfactant, so this is just colloidal titanium nitride particles. And it turns out they hit even more efficiently than gold does. So that's yet another promising applications for this thermal therapy. In this case, you would need to use these colloidal particles made of titanium nitride. But is there any simple way to make these colloidal titanium nitride particles? Remember I mentioned gold, silver. Coming back to the Faraday's time, actually, they did it by using this reduction reaction between two cells. It turns out it's very easy to make titanium nitride colloidal particles, and we demonstrated that. You just buy, for very cheap, next to nothing, titanium particles. Titanium, it's titanium dioxide. And you could buy them of any sizes, and it's very cheap and available. And then you nitridize these particles in the atmosphere of ammonia. You anneal them in the atmosphere of ammonia, and what happens, you basically replace oxygen with nitrogen. And your titanium dioxide particles becomes titanium nitride particles, and they're beautiful. Since the lattice crystal is, since the lattice actually is cubic, therefore they actually look like cubes, because they're single crystal, as opposed to gold colloidal particles, which are polycrystal. In this case, you get single crystal colloidal particles of titanium nitride. Not surprisingly, they look like cubes because the lattice is cubic. So it's simple and elegant way to make these titanium nitride colloidal particles. So yet another application. So I already mentioned this photovoltaics, data storage, and thermal therapy. So nonlinear optics. Now we're coming toward this nanophotonic circuitry. With titanium nitride, okay, it can sustain high temperature. It means that it could sustain high intensities. But how large is nonlinear response of these materials? Because for switching all this type of applications, it's very important that it would have large nonlinear response. And it's known that gold has quite large nonlinear response, quite large nonlinear susceptibility. To measure this, people use so-called Z-scan. Let me not go into details, but it actually measures Chi3, real and imaginary part of Chi3. So what we did, we measured Chi3 for titanium nitride at two different wavelengths, telecom and around 800 nanometers. They're both important, with so-called open aperture and closed aperture, which basically allow to measure real and imaginary part of Chi3. And the result is that in case of titanium nitride, we get at least as high nonlinear response as in the case of gold. And we know that in gold, actually, nonlinear response is high, which is a very good news, because with titanium nitride, you could apply much higher intensity, meaning that you would get much stronger nonlinear response. Since it's nonlinear response, it's proportional to intensity. So if Chi3 at least as high, in some cases higher, and it could tolerate much higher intensities, you could count on much higher nonlinear response. That work done by Nate Kinsey. He was a leading person on this project. So you see this material has all these robust, durable properties, but also it shows pretty good nonlinear responses. Altogether, it's indeed a very promising plasmonic materials for real-life applications. So let's move and overview a little bit, although I did talk about this already, but to speak of these material platforms, and not to mention transparent conducting oxides that perfectly suited for telecom applications, it would be quite an omission. So what is special about transparent conducting oxides? They have very high solubility, meaning that you could actually dope them up to high concentrations, like 5 times 10 to the 21. And that, when you dope it with some metal-like material, actually becomes plasmonic. That's important. So there is very mature fabrication, many different processes ranging from sputtering to PLD, ALD, CVD. And because these materials are known, they're used for screens, displays, they just were not used for plasmonic applications so far. This is non-stoichiometric material, meaning that its properties depend on the way you make it. As a result, you could actually tune plasma frequency in a huge spectral range. Remember, this was like a holy grail to be able to tune plasma frequency, which in gold and silver is just fixed around 9 eV. You cannot do anything about this. Here you could move it in a very broad spectral range by simply changing the charge carrier densities. Like in the case of ITO, indium tin oxide, between 600 and 1600 nanometers. So, indium but that's the ITO involves some rare material actually, and if you think of scale production, it would be a problem. So whereas zinc oxide based materials, which we pursue in our lab, actually it's really cheap and readily available material. And when you dope it with aluminum or gallium, it becomes plasmonic around telecom. So, and that's a really nice plasmonic material. If you now look at the real part of dielectric permittivity, this is gallium-doped zinc oxide, ITO, aluminum-doped zinc oxide. We see that crossover around 1200, meaning that at telecom it's already plasmonic, and dielectric permittivity is negative and reasonable, not hugely negative. And as I mentioned, sometimes it's a problem when it's hugely negative. And if you look at the imaginary part, then it's several times much smaller actually than gold and silver, which means that, at least for some applications, that's really very good. And I pointed out already once that if you walk close to the point when the epsilon crosses 0, it's easy to switch from dielectric behavior when epsilon positive to metallic behavior when epsilon negative, because any change compared to 0 relatively is large, because you basically normalize it by 0. And therefore, you have like metal dielectric phase transition, which could be huge, meaning that the change in optical properties could be quite dramatic. And that's a key thing about optical switching. So in terms of these nanophotonic applications, again, Nate Kinsey wrote this review article summarizing all this type of new materials for nanophotonic circuitry application. And here are some important results in that regard. I mentioned that one of the things plasmonics could be used as an interconnect. Basically, instead of wires for electricity, you use this surface plasmon polariton to send information from one point of a chip to another point of a chip. And so what we did to demonstrate that it's indeed titanium nitride could be used for guiding surface plasmon polariton, we made this strip made of titanium nitride. You see the beautiful single crystal structure. It's really single crystal. That's a big advantage over gold. And we demonstrated propagation length around 5.5 millimeters, which is close to 1 centimeter if you use so-called long-range surface plasmon polariton. That's a truly microscopic distances because we are talking about chip. So in principle, yes. And it's robust, it's single crystal quality, it's CMOS compatible. So we show that titanium nitride could be used for this as an interconnect on a chip. One of the key things is a modulator, because that's about switching. That's a key thing. So we looked at this particular design of possible modulator, which involves transparent conducting oxides and titanium nitride. So it turns out that if you use transparent conducting oxides, as I pointed out, where you could easily switch its properties quite dramatically, basically you could change transmittance of AZO 40 to 30%. Now actually we change it even stronger. So that means that you could quite strongly modulate optical property or your modulator. So in this case, we use titanium nitride as a waveguide. This is your input signal. As a cladding, kind of cladding, or let's say adjacent material, we use AZO. And when you send the optical pulse, you change the optical properties of AZO. For example, you could switch it from metallic to dielectric. And that means that your signal either goes through your titanium nitride waveguide or it doesn't go. That's your modulation. Since you change the properties of AZO and you change it dramatically, so it means that your waveguide for a particular frequency could either propagate that mode or would not propagate that mode. That means modulation. And so our calculations show and measurement actually that modulation is very fast on the scale of 100 femtosecond. This is actually truly spectacularly fast. And that's very promising. And actually we showed that insertion loss in this case would be quite small, 0.06 dB. And modulation depth is very impressive, 0.4 dB per mic. So that's all shows that these materials could find applications for traditional nanophotonic circuitry, which is kind of the main motivation for the whole field of plasmonics. Not only the areas which I mentioned, like energy, data storage, and thermal therapy, but also this nanophotonic circuitry. So let me reiterate. I showed already this couple slides, but today I'd like to look into this in a little bit more detail. So speaking of nonlinearities and switching, this idea that if you work close to the point where epsilon is close to zero, it seems to be very powerful because this is formula from the textbook. I pointed out that refractive index is linear one plus the so-called Kerr effect, and this which is proportional to intensity. N2, it turns out, has linear refractive index in the denominator. If it's degenerate scheme, if it's just one frequency is incident, actually it's linear refractive index squared. If you use a pump and a signal, then it would be refractive index in the first power of this of your signal. But otherwise, if it would be degenerate, you would have even square here. What it means, then if you work close to the point where linear refractive index is small, this term could be very small, whereas this guy would be higher. So you have this kind of like enhancement of nonlinear response because linear refractive index goes to very small values. It's not exactly zero because of some losses, but it could be very small. So you have dramatic difference. And I showed already this plot. In this case, we have change in refractive index actually 5 times larger than linear refractive index, which is very impressive. It could be even higher. I mean, Bob Boyd, who used the degenerate scheme with the same frequency, showed even stronger change in refractive index. It's very unusual that nonlinear term is much larger than linear one. So it's a truly remarkable situation with many opportunities for nonlinear optics and very exciting phenomena. Things which we didn't consider last time when I mentioned this is how fast this response and what is the nature of this nonlinear response. We just recently published this paper where, in collaboration with our with colleagues in Scotland, we showed actually that the time of this response is very fast. So in this case, we would pump with UV light, which basically provides this interband transition in aluminum zinc oxide. And what happens in this case, you simply increase the number of charge carriers because you move electrons from the valence band to conduction band. You increase the charge carriers, the plasma frequency becomes larger. It's a blue shift to the plasma frequency. And as a result, you have this transmittance which drops. And look, the relative change of transmittance is truly dramatic. It's like almost 50%. It's an exception. It's very unusual for nonlinear response to be that large. It's a nonlinear response, and we're talking about change in transmittance like 50%. In liquid crystals, you sometimes have that large response, but they are typically very slow. Here, we looked at the time of this response by doing pump probe experiment, and we obtained it's like 100 femtosecond. It's sub-picosecond response. Such huge change in transmittance reflectance occurring within such short period of time, this is a holy grail for optical modulation, for switching. And actually, it's very unusual for semiconductors to have such a fast nonlinear response. What we believe in this case, what happens, this fast recombination of free carriers goes through these band gap vacancies sitting here between valence and conduction band. It's because of these impurity states, like vacancies. And that's related to so-called Shockley-Reed Hall mechanism. We would not go into details, but that's, we believe, what is the reason why we have so fast response. Because honestly, it came us to a surprise. We knew that the response is so huge in magnitude, but to observe that it's also so fast, it was a big surprise. Normally, the larger nonlinearity, the more slow it is. There is always trade-off. Here, like, both things came together. So that was a pump, a signal always a telecom in this case, or close to telecom. Pump was UV. What if we use pump which is within the conduction band, near infrared, around 800 nanometers? In this case, we were surprised to observe that also the nonlinear response is exceptionally fast, again on the scale of hundreds of femtosecond, the sub-picosecond responses. But the nature why in this case it's so fast is entirely different. When you excite these electrons with the conduction band, you create hot electrons with very high temperatures. As soon as equilibration for electrons occurs, it's actually temperature is high, several thousand Celsius. So, but it turns out that in this case, we believe, because this heat capacitance for electrons and for phonons is very different, and usually like 1,000 times different. It means that the elevated temperature in electrons does not necessarily translate into elevated temperatures in phonons. Because in phonons, dN over dt, refractive index over the temperature for phonons, is pretty large. So nonlinear response for phononic system is large but slow. But because this heat capacitance for electronic system and phononic system is so different, the elevated temperature of electrons does not translate much into elevated temperature of phonons. And therefore, your response is largely electronics, and that's why it's so fast. One way or another, it's really fast. It's again hundreds femtosecond. And again, we obtain this change in transmittance on the scale of 50% relative change. It's truly dramatic. One thing I would like you to note, here it's negative. Transmittance drops, okay, because plasma frequency is blue shifted actually. Here it's positive. Plasma frequency is actually red shifted. You could think of this as kind of saturation effect, because when you excite electrons below Fermi level to these upper states, you populate more and more, and there is like saturation effect. Absorption drops eventually. When absorption drops, transmittance increases. So here delta T is positive, here is negative, which means that if I would apply both UV pump and near-infrared pump, and they have different sign of nonlinearity, I could design and engineer my nonlinear response. And that's truly a beautiful thing, and that's exactly what we did. So you see, this is our signal probe, which is around telecom, and two pumps. One is UV, another is near-infrared. And depending on the delay between the two pumps, I could make this contribution larger or smaller. I could have constructive interference or destructive interference. I could enhance nonlinear response or could change the sign of nonlinear response. I really design and engineer nonlinear response. What I'm showing here is relative change in refractive index. And again, changes a dramatic 30%, not like 0.01%, but like 30%. And depending on the delay between two pumps, you could completely change the size of the shape of this nonlinear response. And that's truly remarkable. So let me sum up these three last lectures where we discussed various material platforms and their applications in the realm of plasmonics and metamaterials. So new material platforms for plasmonics and nanophotonics. So we considered in detail these refractory or ceramic plasmonic materials. And we showed that materials could enable very important applications. They have thermal therapy, like biomedical applications, energy conversion, like thermal photovoltaics and solar thermal photovoltaics, and hybrid thermal photovoltaics. In this case, you take into account they could make frequency selective emitter and broadband absorber out of plasmonic material that can sustain very high temperatures. So data storage, when you could actually place more information in a given area by using this, again, plasmonic materials. Transparent conducting oxides, which are probably the material of choice because of the ability to switch their properties, to change dramatically their plasma frequency, to shift it, and to do it in a very fast manner, which is, of course, very critical. So you could tune and you could tailor the properties of these plasmonic materials. We also considered earlier that these material platforms are critical for future quantum photonics. This is really, we are doing just baby steps. With these Plasmonics Metamaterials, we seem to find material that promise these exciting applications, like these metal nitrides, transition metal nitrides, and transparent conducting oxides. In terms of quantum photonics, it's really not clear what type of material platforms eventually will be used. We overviewed like silicon carbide, silicon nitrides, diamond, quantum dots, and they all have pros and cons. And I pointed out that most probably we would end up with some kind of hybrid platform, which also would probably take advantage of plasmonics and metamaterials, where you could dramatically enhance these quantum properties. And I mentioned some of such applications, for example, using the ideas from metamaterials for single photon sources, when you could generate single photons with very high efficiency, and for quantum registers, when you basically could write and read the spin degree of freedom quite efficiently, using the ideas based on plasmonics and metamaterials. Earlier, we also look at metasurface designs, which this is basically 2D version of metamaterials, which already demonstrated lots of spectacular applications, because in this case, you have a planar version of metamaterials, which is easy to make, and this is chip compatible. And that resulted in a whole family of new optics, flat optics, which is much thinner than conventional optics, because it uses different ideas how to control the phase. Instead of accumulating phase over a large distance when light propagates through bulky optics like a lens or holograms. In this case, you do it abruptly by placing antennas which shift the phase abruptly. And that's an entirely different approach, which enables this ultra-thin optics. And a number of devices already have been demonstrated, like world record thin lenses, holograms, optical plates, cavity spectrometers, and things keep coming out of this very exciting area. Also, what the people now make these metasurfaces conformal and flexible, so you could use it as a wearable optics for all type of sensors. So these metasurfaces could be used for nonlinear active hyperbolic time-varying metasurfaces. Remember that in this case, you break not only photonic momentum conservations, but also energy conservation for photons, because you modulate your metasurface. So that makes it really particularly exciting and enables things like non-reciprocal optics, things like optical isolator, which is yet another holy grail of nanophotonics. So all this together opens up a possibility of chip-based active quantum nanophotonics. So with this, I basically end up this short course within the larger course on this plasmonics, metamaterials, nanophotonics, and quantum photonics.